In this video, we're going to look at the three theories of acids and bases, and they are the Arrhenius theory, Bronsted-Lowry, and Lewis theory. Before we're going to go through one by one, it's better for us to look at how the theory developed since Arrhenius. So basically, Arrhenius was the first person to propose the idea of acids and bases in 1880. And then the idea of acid and bases is further developed by Bronsted-Lowry in 1923 upon realizing that there are a few things in Arrhenius theory that cannot explain some of the basicity and acidity of some species. So from Arrhenius, Bronsted-Lowry developed a new set of theory that complements the theory developed by Arrhenius. So what we have in Arrhenius is further developed by Bronsted-Lowry in 1923. And then what happened next? Lewis had made the acid and base theories to be better, and he added a few more information about acids and bases in 1938. Basically, this is the timeline of how the acids and bases that we have known now, all the theories, they are developed and combined together, and these are the theories that inform how we understand about acids and bases now. So let's have a look at Arrhenius theory first. So basically what Arrhenius is saying over here, acids and bases are classified in terms of formulas and the behavior in aqueous solution. So this is how Arrhenius studied acid and bases in 1880, and he came up with the conclusion that acids are basically substances that dissociates in water to produce H plus ions. So he concluded that based on the experiment that he had done, acids are substances that will dissociate in water to produce H plus ions, or sometimes we can write it as H3O plus ions. H3O plus ions over here is called the hydroxonium ion. Okay? So let's consider this acid that we have in front of you. So basically what we have in HCl is H and Cl that has been dissolved in your aqueous solution. So based on Arrhenius, this species is acidic because what happened? It will donate or dissociates to produce H plus to the aqueous solution. Okay? So this is fitting to what we have in this definition. Substances that dissociates in water to produce H plus. So that is Arrhenius' theory on acid. So he said that this acid, if this species is an acid, it will be able to dissociate in aqueous solution to produce H plus. Apart from writing in this form, we have another way of writing this if you want to show the H2O molecule as part of the reaction. Okay, or what you can write is like this. You can write HCl, aqueous, and maybe you want to add water into the equation. You can do that as well. If you don't want to write it, that's okay. But if you write this H2O in the equation, right now, instead of writing H plus, you're going to write H3O plus in aqueous form. Okay, so this proton H plus is the same as H3O plus. It's just that when you are including H2O inside your equation, you have to write H3O plus now. Why? Because the H plus is taken by the H2O to form H3O plus. If you look, before the reaction happens, in your H2O you have 2H, but after the reaction happens, you have H3 here. Why? Because the additional H comes from the HCl. And yes, this one is Cl minus. We have another example here. If you look at this example, this is the example of a strong acid. When we are dealing with strong acids, the equation will be irreversible, non-reversible process. And why is that the case? We will tell you about that one later. Okay? So what we have here, this is the example of a weak acid. So when we have weak acid like CH3COOH, we're going to be using the reversible arrow like this. But the concept is still going to be the same. You're going to have H plus going to be produced because this is based on Arrhenius. And you have the CH3COO minus species as well. Okay? If you want to write that with the presence of water in your equation, you can do that as well. Just like what we have done with HCl. And you're going to plus with H2O liquid. So this time you have H3O plus. So remember, H plus and H3O plus, they are the same thing. It's just that when I want to write my equation in this way, because I want to show H2O there, then I will write H3O plus. But if I do not want to write H2O inside my equation for Arrhenius, it's okay for me to just show that H plus is dissociated in the aqueous solution. And over here, you'll have the same thing, CH3COO minus aqueous. So the difference now is the type of arrow that I'm going to use for this reaction when I want to write the chemical reaction. Since CH3COOH is a weak acid, then we're going to use the reversible arrow. And for strong acid like HCl, we're going to be using the irreversible arrow. Now, what about bases? According to Arrhenius theory, bases, they are substances that dissociates in water or aqueous solution to produce OH minus ions. Okay, OH minus, the name is hydroxide, so you can pronounce this as hydroxide ions. So it's completely the opposite as acid just now. Acids are substances that will be able to dissociate in water to produce H plus. Now, for bases, it will be the one that's going to be producing OH minus. Let's consider this example. So your basis over here, NaOH, as you can see, we have OH, and this one also has OH. Obviously, NaOH and BaOH2 will be able to dissociate in water to produce OH minus. Since both of them are strong base, okay, so both of them are strong bases, we're going to use a reversible arrow. So you will dissociate, it will dissociate to form OH minus. And the positively charged species. So when you have OH minus is produced, meaning NaOH is a base according to Arrhenius theory. Right here we have 2 OH minus. We have 2 because you have 2 right there, so be careful when you want to balance the equation. And plus Ba2 plus aqueous. Way to remember this: acids is the one that will produce H plus or proton. The other name for this is proton. H3O plus, the same thing, hydroxonium ions. And bases are those producing OH minus ions, according to Arrhenius theory. So this is a tip for you to remember. What does it mean by acids and base, according to Arrhenius theory? What about bases like NH3 here? NH3 is a very well-known base, but if you take Arrhenius theory, all of the explanation that we have learned just now, NH3 does not fit in the definition. So what about base like this? This is the reason why we have the development from Arrhenius. If you still remember, if we're going to go back to the page over here, this is because from Arrhenius, Bronsted-Lowry realized that there were limitations in the Arrhenius theory. Therefore, from that limitation, Bronsted-Lowry develops a new set of theory to complement what we have in Arrhenius. Don't get confused. Bronsted-Lowry, the theory is not try to cancel out Arrhenius, but the reason why Bronsted-Lowry wanted to develop a set of new theory because they want to complement what we already have in Arrhenius theory. Okay, so according to Bronsted-Lowry, species like this are also bases due to a few things. So what happened here, Bronsted-Lowry in 1923, they have widened the concept of acids and bases in the acid-base reactions. And how did they do that? So instead of only focusing on who will be donating H plus, who will be donating OH minus, they were focusing on the proton transfer between the acids and base. So that's why the theory is able to develop the existing theory even further. Now, based on the Bronsted-Lowry theory, acids are substances that can donate a proton to the base. At first glance, the acids theory based on Bronsted-Lowry sounds similar to what we have heard in Arrhenius just now. But you need to remember, in Arrhenius, we are focusing on what happened in the water when you dissolve the acid. And when the species is able to donate H+, is able to dissociate and produce H+, according to Arrhenius, that is an acid. However, in Bronsted-Lowry theory, acids they are focusing on the ability of the species to donate proton H plus to a base. So it doesn't really matter if your substances are going to be dissolving in water. According to Bronsted-Lowry theory, that species can also exhibit the characteristic as an acid if the species is able to donate a proton H plus to a base. So what about bases according to this Bronsted-Lowry theory? I think you can guess already. It's going to be the opposites of what we have in the acids just now. So basically, Bronsted-Lowry theory states that bases are substances that can accept a proton H plus from the acids. As you can see, it's just completely the opposites of what we have over here. So it's quite easy to be remembered for Bronsted-Lowry theory. Acids is the one that will be donating H plus, and bases are those going to accept the H plus. Why can they accept the H plus? Because they have lone pair. Now let's consider this reaction over here. We have HCl. We do know that HCl is a strong acid. This is your acid. Okay, we know that this is your acid. And then in your acid here, you have H, and that H will be able to be donated to your water. In this case, your water will behave as a base. Why? Because the acidic property of HCl is higher than water, and therefore water will behave as a base. And this base will accept the proton from your acid. Okay, we have Cl minus. Now it loses the H, and we have the H2O. We have one lone pair left, but it will take the H. So this one will be positively charged. Okay? So acids, the Bronsted-Lowry acids will donate the proton here to your base. And as a base, this is a Bronsted-Lowry base. It will be able to accept the proton from the acid. So you can see that the process is going on like this. This one will give, and water will take the proton. Same goes to weak acid like this. So this is strong acid. We have another acid, but this one is considered as weak. So when you have weak acid, we're going to use reversible error like this. What happens? The proton, this proton here, will be donated by the weak acid, and it will give it to the lone pair of your base. Water still is behaving as a base. And you will be producing CH3COO minus aqueous plus, and yes, you're going to have your H2O, one lone pair left, and the other one will take the H, and you have a plus charge on the oxygen. Okay, so I'm just going to put plus charge like that. This proton donated to your lone pair, and you get your reaction like this. So let's have a look at another examples. We have, obviously, this is your acid. And this is your base. Because it has a lone pair over here, and the basic property for NH3 is higher than HCl. HCl has higher acidic property, therefore HCl will behave as an acid, and the proton from the HCl will be donated to the lone pair of your base over here. Since we're dealing with strong acid and weak base, this is strong acid, and then we have weak base. We're also going to be using reversible arrow like this. So we have Cl minus aqueous plus NH3. Now the lone pair has gone because it will accept the proton from the acid, and your nitrogen will have a positive charge. Okay? Same goes to this. So right now, since this is your base, okay, it's a weak base, but still it will be even more basic than water. Water will be the acid. Okay? So water, as you can see, can behave either as an acid or a base, depending on the partner of that water. That is what we call as the amphoteric nature of water. So we're going to use reversible arrow because we're dealing with a weak base. So water will dissociate to form the OH minus. And as you can see, your base right now will lose the lone pair, and you will have this proton, which is part of the water in the beginning. Now it's no longer part of the water. It will be part of the NH4 plus here. So the plus charge will be right there. Right. Now, way to remember Bronsted-Lowry theory. It's quite easy. Acids are proton H plus donors, and bases, they are proton H plus acceptors. It's quite easy. Moving on to the third theory, Lewis theory. So this one is the latest theory among all of the theories that we are learning now. From Arrhenius, we have moved on to Bronsted-Lowry, and then now Lewis. So Lewis was the man that had developed the theory even further. He proposed a much wider definition for acids and bases. So what did he say? So basically what he says over here, based on the transfer of electron pair. If Bronsted-Lowry is talking about one is going to be accepting proton, the other one is going to be donating proton, for Lewis, he focuses on, okay, so this guy focused on the transfer of electron pairs or lone pair. We do know that molecules that can have lone pair, so when that lone pair can be transferred, that also can determine who will be acids and bases. So basically, based on Lewis' theory, acids are substances that can accept a pair of electrons. Therefore, they will be forming a dative bond. substances that can accept a pair of electrons. Different from what we have done in Bronsted-Lowry. In Bronsted-Lowry, acids are species that will donating proton. For Lewis theory, acids are substances that can accept a pair of electrons. These are the examples of Lewis acids. We have BF3, AlCl3, and even H+. So it fits in the other theories as well. H+ in Arrhenius is the indication of acidity as well. And then H+ in Bronsted-Lowry is also an indication for acidity as well. And when we get to Lewis theory, H+ is also an acid because it will be able to accept a pair of electrons. So they are mostly incomplete octet molecules. BF3 is incomplete. AlCl3 is also incomplete. And this one is also incomplete. Mostly going to be incomplete octets. Why? Because they need to have empty orbitals to accept pair of electrons. If you do not have empty orbitals, you will not going to be able to exhibit the characteristics of becoming Lewis acid. Bases, on the other hand, according to Lewis theory, are substances that can, if you can guess, yes, it will be donating electron pair. Instead of accepting, bases are something that can donate lone pair or electron pair. If you remember in Bronsted-Lowry just now, we were talking about the examples of water as an acid reacting with your ammonia NH3. The NH3 just now that we were talking about, if you still remember, just now you have this NH3. This is a base. We know that this is a base. According to Bronsted-Lowry, this is a base. And then according to Lewis theory, NH3 is still a base. Okay, because you have a lone pair over here, and this lone pair can be donated to an empty orbital. Now let's consider this. We have a Lewis base, NH3, with a lone pair or electron pair. And we have a Lewis acids, BF3. Okay, this acid over here, if you look carefully, if you put this into Arrhenius theory, it will not going to be classified as an acid, but the reality is this is an acid because it will be able to accept this electron pair from the ammonia. So what happened when they combine together? You will be forming dative covalent species. Okay, this lone pair will be donated into the empty orbital of boron here. Then you will be forming this. Okay, and that's in the middle is your dative covalent bond. Okay. Another example is this. So we have Lewis base, which is water, and Lewis acids, which is H+, because water over here has two lone pairs, and one of them will be donated to your H+, and then your Lewis acid will be accepting that lone pair to produce this structures over here. So way to remember, Lewis theory, acids are electron pair acceptors. Bases are electron pair donors, according to Lewis theory. Some important points. Number one, we have to remember, always keep in mind that the three theories that we have learned just now, Arrhenius, Bronsted-Lowry, and Lewis theories, they're always going to be working together to define acids and bases. They will never gonna be confliction. Okay, they will never gonna be conflicting one another. They will work together as three theories that will be working together to inform our understanding of acids and base. That is the most important thing that you need to keep in mind. So you don't have to worry. If one thing is acids in Bronsted-Lowry, it will also going to be an acid somewhere else. Okay, they will never going to change the characteristic based on the theory. It will always going to be an acid. But we only have the only thing is we have three theories that had developed from Arrhenius until Lewis. And right now, we're going to be using all of those theories to understand the behavior of acids and bases. Second, water, H2O, is amphoteric. Amphoteric, like what we have talked about just now, amphoteric is behaving as acid and base. So it has both characteristic of acid and base for H2O. And to recap in a nutshell, so the theory developed from Arrhenius, okay, the first person to develop the idea of acids and base. In the beginning, it says that species that will produce H plus will be acids, species that will be producing OH minus will be base. But then again, when they do more research into it, Bronsted-Lowry realized that they are species like NH3. They do not have OH minus, but they are bases. The reason is because bases are proton acceptors and acids are proton donors. And then, thirdly, the acids and bases theories are developed even further by Lewis' theory. And then he says over here, acids, they are electron-pair acceptors, and then bases are electron-pair donors. This is how the theory developed. And now, in our modern thinking of acids and bases, we are using all of the three theories here to understand acids and bases.